Hello everyone, welcome to today's talk. This is Weida Zhong, a PhD student from University at Buffalo. Today I'm going to present our work on heterogeneous spatial-temporal graph convolution network for traffic broadcasting with missing values. Let's get started. In our work, we consider the following traffic prediction definition. Given historical traffic information like traffic volume, traffic speed, or various road segments, we want to predict traffic conditions in the following timestamps. In this paper, we only consider the near future as far as 90 minutes. The first two pictures show the traffic condition of downtown Buffalo at 4 p.m. and 5 p.m. respectively. The question to answer is what the traffic condition will be at 6 p.m. If we know the future traffic condition in advance, then we can plan our travel accordingly, which may save time spending on the road. Since traffic prediction is an important task, there have been lots of work on it. Traditionally, data collected from stationary sensors like traffic cameras and loop detectors are used, but due to factors like high cost, only a limited number of stationary sensors have been deployed, which cover limited areas. But different areas have different values and features, so we cannot directly use them to predict traffic conditions on other areas. With this exploration of smartphones and crowdsourcing tools like Weida, it's now possible to collect GPS data easier than ever before in much broader areas. This could promote the development of the intelligent transportation system, which could further reduce traffic congestion, increase the driving safety, and so on. Compared with stationary sensors, however, using roving sensors data for traffic prediction brings new challenges. The major challenge we are dealing with in this paper is data sparsity. In other words, we don't have traffic data for all roads at all timestamps. The figure illustrates this situation. In this figure, each line denotes the traffic volume for each lane. Not all traffic volumes for all lanes are available at all times. One key observation in addition to this challenge is that the relationship between roads changes along with time. One single graph may not handle all cases very well. So our solution to this data sparsity is to use bidirectional recurrent neural network to carry out the imputation. And our solution to the changing relationship is to build heterogeneous graphs. I will talk about the imputation and the heterogeneous graph in details in the following slides. Here is an overview about how the framework works. The input data goes through a heterogeneous GCN and LSTM module. Each HGCN consists of a geographic graph and temporal graphs that are built upon historical data. The output of the current timestamp is used to replace the missing value in the following timestamp. This process is shown in the right figure. Here, the first figure will only show the forward path. The backward path is exactly the same, except that we use reversed input. Here is an example of different relationship among nodes in terms of geographic distance and historical data during different periods of the day. In figure A, there is almost no connection between node 2 and node 0. However, in figure B and C, node 2 and node 0 have demonstrated strong connections. The graph based on geographic distance is straightforward to build. So next, I will talk about our methods to build the temporal graphs. In order to build temporal graphs, we first need to divide the timeline into non-overlapping intervals, and then build a graph for each individual interval. So how to divide the timeline? Let's first assume we know the number of graphs that we want to build. Then we want to maximize the overall distance between intervals. Here we define the difference between the two intervals as the distance between their historical measurements. In addition, we apply constraints to avoid trivial solutions. One example of these constraints is that the minimum size of any interval cannot be smaller than 1 hour. In this paper, we choose m empirically, but we can try different m to maximize this maximum. Lastly, I want to briefly talk about the datasets that we use in the experiment. The first stampede dataset was collected by 15 stampede shuttles, whose route has been depicted in the leftmost figure. The second picture is an example of the deployed smartphone in the overhead bin of the stampede shuttle. The collected data is transferred to our server through the campus Wi-Fi. In addition to the stampede dataset, we also use the PMS dataset, which is widely used in traffic prediction. We randomly remove some data to simulate the data missing scenario. We carried out extensive experiments on these datasets, including prediction performance with respect to prediction length and missing value. Please refer to the paper for more details. Thanks for being here today. Please feel free to send an email to me regarding any questions about this paper. Thank you.